Hi, this is Mr. Barron. We're going to be reviewing how to classify matter. In classifying matter, we have to talk about what matter is. And of course, the thing that you've probably learned before is that matter consists of different states. Among those states are solids, liquids, and gases. And you've probably heard about plasma before, which is sort of that state of matter beyond gases, where the atomic structure of atoms really can't hold together. But for this class, we're really only going to focus on solids, liquids, and gases, particularly that solids have a rigid, fixed shape, and liquids fill the shape of their container, but they have a very definite volume, and gases have no fixed volume or shape. You can change the volume based on other properties like pressure and temperature. In a gas, we need to know that the particles are the furthest from one another. That's how they're able to take the volume of the container. Just think of a balloon. They fill up the size of the balloon, and that's dependent usually on how much gas you actually have. So this is a visual representation of what I'm talking about in terms of taking the shape of the container as opposed to taking the shape and volume of the container. One of the things that we need to know is that light, electromagnetic radiation, is not matter. Anything that we see is not made of atoms or subatomic particles. They come from atoms and subatomic particles, but it's really just a form of energy transfer. It's not the atoms that we've known about in your other classes. So just to take a little trip down element road, stuff that you've learned before in other classes, we're going to play a song from this top website right here. It's something that I hope that you can hear on the audio of this presentation. So here we go. So what are the elements? Let's find out right now by playing this.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Alright, so we've got lots and lots of elements. I hope you could hear it. If you couldn't hear that song, of course you can type in this address right here at the top, and you can play it for yourself again. One of the reasons I'm playing is that this lecture is about classifying matter, and one of the ways that we are able to classify matter is by what elements make up matter. Not just what state they take, meaning solids, liquids, and gases. I used to joke with students that if you could sing the song exactly as you heard it, I'd give you an A straight in the class. So do we need to memorize all of these elements? Well, no, that's why we have this thing called a periodic table, which of course you've seen before. Why do I not make you memorize everything on the periodic table? Well, that's because of the 90 elements found on Earth, only 25 or so are used to build all living things. If you look at the human body is mostly hydrogen, then oxygen, then carbon, then nitrogen, then everything else is just a fraction of a percentage of our own bodies. So when it comes to the elements that we're studying in this class, we're really not going to be focusing on every single element. So even I have not memorized all the little inane details of the periodic table. So what is matter made of? Well, you may want to pause this presentation and write down everything that you see on this slide. This is a review of everything that you should have learned in middle school about chemistry, particularly that light is not matter, atoms are discrete particles, elements can be one or more of the same atom, compounds are a combination of bonded atoms, and of course bond we're referring to, quote, the glue for atoms, the forces that make them stick together, and a chemical formula shows you how many types of each atom are bonded to form in a compound. So now, counting atoms. for each element in a compound. We should be able to look at a chemical formula like H2O and know that chemists are lazy, so we don't write ones. There's a reason why it's not H2O1. When there's no number next to an element symbol, it of course just means 1. So there's 2 hydrogens and 1 oxygen for the formula H2O. Sometimes we don't combine the element symbols. So you'll see that the hydrogens are separated from each other. So in this case, you have to add the 3 hydrogens to 1 hydrogen to get 4 hydrogens. So in this one, you have 2 carbons, 2 oxygens, and 4 hydrogens. Now I need you to know that there's parentheses. Parentheses are usually used around what are called polyatomic ions. And nitrate, NO3, is a polyatomic ion. When you put a 2 to the bottom right, it means that everything inside the parentheses is multiplied by 2 because you have 2 NO3s. The 2 out here does not apply to the copper. So in this case, you still only have 1 copper, but we have 2 times 1 nitrogen, that's 2 nitrogens, and 2 times 3, that's 6 oxygens. So, little practice. I want you to do the self-check with me. How many nitrogen atoms are in NaNO3? Well, you should be putting 1, because there's no number to the bottom right of nitrogen. How many oxygen atoms? You should be putting a 3, because there's a 3 to the bottom right of the NO3. How many oxygen atoms? Well, we have the parentheses, so we need to know that there are, make sure you count, 2. Okay, how many hydrogen atoms are there in this one? I'll give you 3 seconds. All right, hopefully you put 8 because this 2 on the outside multiplies everything on the inside. All right, now we're going to be doing a number of labs where we're recording observations, and those observations are typically on either the physical properties or the chemical properties. This is something you need to write down in your notes. Why don't you pause the presentation and copy this down, then read it, please. All right, let's check what you've copied down. The boiling point of alcohol is 78 degrees Celsius. Is this a physical property or a chemical property? Get it in your mind, look at your definition. Hopefully you put physical. Let's do another one. Diamonds are very hard. Physical or chemical? Physical. Sugar can ferment to form alcohol. Chemical. Remember, anything that involves changes, chemical changes, is typically a chemical property. Metal wire conducts an electrical current. Physical, because we're not talking about the actual chemical structure of the metal changing. This slide that you're watching right now is white. Physical. Platinum does not react with oxygen at room temperature. Chemical, and the reason because we're talking about reactions, changing. All right, let's talk about physical versus chemical changes. Let's take a look at water for a second. Let's look at how the structure of water is affected by both physical and chemical changes. So here's water, and this is an example of a physical change. You need to pause the presentation and copy this down. See, atoms are not rearranged in physical changes. So if you have solid ice, then you melt the ice, notice the structure, the chemical structure, how the bonds are arranged of water does not change throughout these physical changes. Now chemical changes, the atoms are rearranged. With water, we can send an electrical current through it, and it'll actually break the bonds between the oxygen and the hydrogen and form new ones between each hydrogen and each oxygen atom. That's what we call a chemical changes when the atoms are rearranged. Pause this and please record this down as notes. All right, chemical equations. We use chemical equations in chemistry to describe chemical changes, not physical changes usually. In the case of this picture showing the chemical change to water when we run electricity through it and we break the bonds and we form new ones, what we have is a chemical equation describing the picture above. We use coefficients to describe when we have more than one of the same molecule. So in this case we have 2 molecules of water, and this L here represents that it's in a liquid state of matter. The G's over here represent the gas state of matter. So we have 2 hydrogen molecules produced that are gases and 1 oxygen molecule produced that are gases. So these numbers in front are coefficients, and it describes how much of that particular compound is used in the change. And we're going to start calling these things, these changes, not chemical changes, but chemical reactions. That's the word we want to use in this class. The chemical formula we learned about before. Don't forget states of matter, where we're going to be working mostly with gases, liquids, and solids, but another one in the future as well, called aqueous. We have the reaction arrow, and then everything before the change we call the reactants, and everything after the change we call products. Remember, reactants react to produce products. So how do we know when atoms are being arranged and we're seeing a chemical reaction before our eyes? We have a lot of different things. If there's a color change, a solid precipitate forms from two aqueous solutions. Look at this aqueous solution and this aqueous solution. When I say aqueous, it means you have a compound that's dissolved in water. So we have two compounds that are dissolved in water. When they react with each other, they form a solid, and that's a solid precipitate. In this case, it's lead sulfide. So color change, solid precipitate forms if you see a gas evolve, bubbles, but not the type of bubbles, of course, from a physical change like boiling water. And then if something gets colder or it gets warmer, energy is released or absorbed. Let's self-check ourselves now. Iron metal is melted. Is it physical or chemical? Good, physical. Iron combines with oxygen to form rust. Chemical, because we have a change occurring. Atoms must be rearranging if iron's combining with oxygen. Wood burns in air. Chemical change. We know it's a chemical change because we have light produced. You have a lot of different signs of the chemical change, actually, when you have wood burning. Rock broken into small pieces. Physical change. That's the end. If you have any other questions, please let me know.